5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Cailabs is a French laser company, and one thing they're doing are optical communications between Earth and space. This has a number of advantages over radio frequency communications, which is why it is being adopted by customers, for example, in defense. The company also just raised 57 million euros in a funding round. Founder and CEO Jean-François Morizur is our guest. Enjoy.
My name is Raphael Rodkin. I'm the founding partner of E2MC, Earth to Mars Capital, a venture capital investor in dozens of space startups worldwide, among other roles I have, such as being a part-time podcast host. Just as a reminder, this podcast is for informational purposes only. It does not reflect any view by E2MC, and nothing should be taken as investment advice. Before we start, a quick favor. If you do enjoy this podcast, please leave us a 5-star review on your favorite podcast app, such as Apple or Spotify. It does help other people find the podcast. Now on to today's episode.
Hey, space enthusiasts, welcome back to another episode. And it's with a really cool space startup from, well, not only space actually, as we'll talk about, but a really cool startup, later stage startup from Europe, from France. It's Cailabs. And I'm super happy to have their CEO and co-founder, JF Morizur, here today. Welcome, JF.
Well, thank you very much. Thank you, Raphael, for inviting me to this podcast.
And thank you for doing this. I've been looking forward to this for a long time. And thank you also, like speaking from an American perspective, for doing this on Halloween. It is Halloween today. Yes,
exactly.
I should have sent out a message before that we all dress up, but you know.
I didn't do. Yeah, sorry about that.
No worries. But JF, why don't we start as always? And could you give us sort of the summary, the elevator pitch on Cailabs, please?
Yeah, of course. So Cailabs, what we do is we make optical ground stations. So it enables you to have optical connectivity to satellites rather than just radio. And that from the ground, as the name entails, it says you're able to make that connection between satellite and the ground with lasers. We are a 160 people company. We are based in France, as Raphael, as you mentioned. We're based also in Washington, D.C., and we're expanding and going around the world. And those optical ground stations, they are starting to be deployed in multiple locations. So it's amazing now to see them pop up and to see them connect with satellites and all of that. So that's what we're going to be talking about.
Terrific. And so, since we're always saying we're a non-technical podcast, I'm going to take a step back here. And so it's probably obvious to most of our listeners that satellites, yes, they have to talk to the ground, because otherwise, what's the use of, whether it's a satellite communication satellite, but if you're long distance video or phone call or something like that, there you have to go back from ground and back to the ground. Or, of course, what we call Earth observation and remote sensing, where you image the Earth, that also has to go back to the ground. Actually, as an interesting historical note, some of our probably younger listeners may not be aware that before we had ground links, the Earth observation satellites actually were taking the images on film and dropped them back into the atmosphere.
Hey, I did not know that.
You don't know that? Yeah, the first spy satellites, literally they dropped like cylinders with like film inside back into the atmosphere, and they got picked up by planes, basically. So
really?
Yeah. See, you disrupted this market. And the radio guys disrupted this market, and now you're disrupting the radio guys. This is progress.
Yeah. I think the communication from satellite to ground is this is what we use satellites for, basically. If you don't have communication, what is satellite useful for? I mean, people talk about space manufacturing, but this is a small part of the business and small part of the value that space brings to us. It's not to say that in the future we won't have more space manufacturing, but at the moment you're basically getting information from your satellites. Either it's information produced in space, so as you said, taking pictures for intelligence, or is it information that is carried through space? I mean, just going up from another location on the ground, going and down another location, just carried through space. So that's it's the main value of the satellite is the information that's been given to the ground and taken from the ground, and it's done with radio most of the time. And what's interesting is we're seeing a lot of situations where a radio has reached or is reaching some limits. It can be limits due to a conflict, because radio can be jammed, radio can be intercepted, radio can be detected. And so in those contexts where detection, interception, jamming is really something you're afraid of, then optical is another way to go. The same thing happens if you've got spectrum issues. In order to communicate on a given radio band, you need you need to have the right to do so. Otherwise, you would interfere with all the others. Yep. And so if you don't have this right to use spectrum, then you need to buy it from somebody else or rent it for somebody else or file for that. But basically, if you don't have it, then maybe you need to go optical, because that's an alternative way where there's no spectrum question, because there's no interference, basically. Two laser beams don't interfere with each other, at least on the normal geometries. And then finally, there's the question of bandwidth. And this is something that, people, when you've got congestion where you would want to carry more information faster, well, you can always cram more information through a radio signal. And there's a limit. And there's actually a very painful limit called the Shannon limit. I'm not sure how, that gets to be technical, but basically it's it becomes exponentially more difficult to cram more bits per second with the Shannon limit. And it's related to the bandwidth, it's related to a lot of things, but it's basically within the given, frequency, within some fundamental limitations, you in order to cram more data, it becomes exponentially more costly in terms of power or in terms of amplification, whatever it is. And exponential is costly. It's basically means every time you do that, it's a factor that you need to do that. And so optical is a way to completely, bypass that, sidestep that. So if you're reaching a point where you're hitting those Shannon limits, then optical is the way to get away from that. And that's kind of the main driver. And I'd say it's like you're saying, disrupting. I don't really like that word, because it's been used too much in a lot of industries. So I'm just saying it's a complement. Optical is a good complement to radio in some context. It's a very relevant one now, but it's in some context.
Yeah, and I mean, you said a lot of interesting things there.
Sorry.
This is great. You hit on a lot of points I was going to ask you about anyway, because that has been my thought, that it's much more secure because it can't be jammed. It's literally this, in some of the sci-fi novels, they even call it the tight beam, right? Because
it is definitely
it is literally a tight beam.
It is. Well, actually, in order for people to picture it, if you've got a satellite that's LEO orbit, a typical beam of radio wave on the ground is about 40 kilometers. That's wow. What you can get to. So that's the tightest you can get. I'm pretty sure you can, a normal, that's just rough sizing. The tightest, the equivalent on the laser beam is tens of meters, and it's due to the physics. So within these 40 kilometers you can intercept, for example, or you can detect the beam. In order to intercept and detect a laser beam, you would be within those 10 meters. And as we discussed it with some of the, especially military guys, they say, well, if I've got somebody who can intercept my beam in, 10 meters from my ground station, honestly, I've got another problem, because you can throw a grenade then, or you can probably, come in and actually take
out your knife or whatever.
Yes. When you, knife distance, your problem is a little bit different. So this is kind of, when you say exactly, it's tight beam, and it's the ratio is massive, and it's even larger when you go further away.
I was going to say, it sounds like for interplanetary type communications.
Oh, no, yeah, it's impossible to sorry, no, it's not impossible. It's a very valuable way to do it. If you can do it with lasers, you actually, because the beaming gets narrower, you get far more, the transmission rates are much better. Today, for interplanetary distances with radio, you've got all this kind of issue with power and very, very low data rate, because you've got it's so spread out. And lasers is a good option for that. There's actually a lot of projects working with lasers for very long distance. But that's very I don't want to represent lasers as being something, a space exploration thing, because today you've got lasers between satellites and they are heavily used, and it's for you and me. If you've got a Starlink antenna, your data goes through laser beams.
No, absolutely. That's got to be your biggest market is the current constellations. Fully understood.
Yeah, and we keep in mind, we don't do satellite we don't do the terminals in space. We do the one on the ground. So, but I want to for the listeners to be careful that you don't need to represent yourself that lasers is something like either Star Wars, science fiction-y, or whether it's something like space exploration. It's already deployed in commercial industrial scale for constellations today.
Yeah, so this is actually bringing up an interesting point. So we should lay this out for our listeners. So it's mostly deployed, correct me if I'm wrong at the moment, for inter-satellite links. So you have I guess a pair of satellites. It could be more in orbit, and they talk to each other. And for example, SpaceX in its Starlink constellation, I think all of these satellites are basically linked via lasers. Whereas what you are doing is going between space and ground. And then, by the way, I guess the other type of lasers, I guess there are some companies also doing ground to ground with lasers, right?
Yeah, they do. Yeah, definitely. Yeah.
Okay. But then you're doing between space and ground, and that, well, we've had many conversations about this. This is a particularly difficult problem, I guess. And can you kind of explain high level why that is?
Yeah, and basically when you start with that, you think, oh, it's going to be, space to space and space to ground is going to be similar. I'm just going to, go through the atmosphere. Maybe the atmosphere gives me a bit more loss, but it's going to be okay. Actually, it's not. That's the issue. It's because the atmosphere it's not just, it's not just cloud coverage. A laser beam, they don't go well through clouds. And so you would say, oh, I need to wait for some time when there's no cloud, clear blue sky. But that still doesn't work because the atmosphere plays with the lasers. Like the shape of the lasers is there's a little bit of absorption, so there's a little bit of your losses because the light is absorbed by the air. But there's something which is far more problematic, which is the shape of the lasers is modified by the interaction with the masses of air. And this is kind of, you can see it if you're looking at the sky with your own naked eyes and you look at a star and you say, you see twinkling, twinkle, twinkle, little star. This twinkle is like the star itself is a big ball of fire. It's very, it's very stable. This thing is the relationship between the light of the star and the atmosphere, and then your eye that just detects a part of that light from the star. And so that's the same phenomena you've got with the laser beam going through the atmosphere. You've got this twinkling effect. We call it deep fading because there's, you don't want to use a twinkle kind of word. It's too much like a, but fundamentally it's twinkle. And so you've got this communication channel that twinkles, and you need to remove this twinkling. And this has been vexing people for quite some time. So there was different approaches, different challenges, and it turns out that we had a product, like a solution that we used for telecom application within fibers that was useful to remove that twinkling. It was actually originally some Japanese clients that told us you should look into that, and telecom clients. And then we started by doing a system proof of concept that said, can we remove the twinkle? Yes, we can. And then from that, it was like, okay, let's actually build a full ground station that integrates this. And this is where we are today. But that's kind of how we got to that point. But yeah, this is the main difference between SAT to ground and SAT to SAT. SAT to SAT, there's no air, so you don't have any issue with twinkling or thing like that. And SAT to ground, there's this issue with the air, the atmosphere. And you could try to remove the atmosphere, but typically we like to breathe. I think that's a fundamental need for humans. So that's not really a good option. And so we need to work with the atmosphere. And
it'll be easier on the moon.
Yeah, oh, definitely. Yeah, I mean, moon to satellite is equivalent to satellite to satellite. Yeah. And so I agree 100%. I mean, it's more like at some point you need to cross the atmosphere because us human, we live on the ground, basically.
Yeah. And so the removing of the twinkling, it sounds like you found for the lack of a better word, like a hardware type solution to it. Remember, I'm not a technical guy, so I may say stupid stuff. But sort of like, I guess the twinkling, technical word as well, right? I guess it would mess up the information content, right, of the beam, right? And so my question was going to be, is like, besides the hardware, is there something like you could also do algorithmically? You know how like if you show like a jumbled word to a human, like our brain basically is capable of adjusting it to the correct information.
So that was kind of, I mean, obviously everybody wanted to do that because that's the easiest way forward. Like, you detect it as if there was no twinkling, and then you would put all that into a computer and you get away, get out with it. And the problem is the nature of the twinkling and the nature of what happens. It's what happens. You've got deep fade. You've got moments we've got absolutely nothing, and that actually, and those moments tend to be quite long. I mean, long in the context of communication channels. So it's not like it's milliseconds and tens of milliseconds, but that has a lot of impact on your beam and on your latency and on the memory. You need to resend things and stuff like that. So there are a lot of protocols. Some of them is basically when you're receiving something, you're missing some information, you need to ask again the satellite to send it back. The problem of doing this is that you need to keep that in memory, obviously. Otherwise, they need to keep it in. So if you're doing a telecom channel, then you've got an issue because it means that you need to have a massive buffer. If it's if I've taken a picture of the Earth, you could say, oh, that's okay. You store the picture for a longer time and just ask again. And even that is a little bit complicated because it's more like accessing memory and anyway. But then if you're doing telecom, you typically don't store. I mean, like your telecom system don't store, this massive amount of data. And so this like, size of the buffer, I mean, how much computing you need to do this kind of protocol. Or you can protect it and it's called something called interleaving, which is like you create some kind of pre-error correction and then you do error correction at the end. But with the type of error you're generating through the twinkling is actually quite very heavy on this. And so obviously it would have been the easy solution. It would have been something everybody would have wanted that. And the reason why it was not deployed earlier is that because it doesn't work that well. And that's why you need to go to optical and to hardware-based solution.
That makes sense.
Yeah, I mean, it's a lot of things in the industry is a little bit like that. Like you will always try first the easiest way to get away from the problem. I mean, obviously. And if you reach a point where you need actual like hardware, optical way of dealing with the problem, it usually means that, yes, there was something that you could not solve with just algorithm. And sometimes you can have very smart algorithm, but today you've got so much computing power, so much availability of algorithm that anything that can be solved with an algorithm is already being solved. Sorry. We always start that. You always start with that, basically.
Right. Now, that makes a lot of sense. Also, if you're starting to mention like going back to the satellite and asking again and buffering, I can see how like for anything that's like two-way, like I don't know, calling or video gaming, that's just not going to be. It's not going to be good.
And I mean, it's like, and it's okay. Like for some situations, why not? But it also reduces a lot your data rate. So if you have to ask again and again, it depends on the size of the packet. But if you say, oh, I've lost that packet again. And the full packet, so you actually, you reduce the ratio of the actual speed, it actually goes down. So I find it very interesting, like all the dynamics to actually get to a working link. At the moment, we've got error-free links with, LEO satellites and with terminals that the terminals or the lasers in space, that these are the same ones that are used for satellite to satellite. So basically, it means that you don't need to have a specific terminal. You don't need to have like a crazy new stuff that you need to qualify. You can leverage the ones that are already existing, that are already deployed, and they can be pointed down to the ground. And all the complexity of the twinkling is dealt with on the ground.
Okay, gotcha. Let me take a step back again, sort of historically speaking. So, I mean, you've kind of, I think, very clearly laid out the advantages of optical communications. Now, lasers, I think, were invented sometime in the 60s.
Yeah.
So it's a long time ago. So why has it taken so long for this to become adopted, you think?
I mean, you could ask the question of, I mean, it's difficult engineering. So it's been ongoing progress. There's been a lot of tests of lasers in space, but it was, you start by doing exquisite test, then it becomes exquisite like commercial, systems like EDRS, the European Data Relay System, that was involving some lasers between GEO and LEO. And then, between satellite, you've got people going into high volume and then basically this topic of going satellite to ground was always kind of challenging. There's a lot of demos, a lot of tests. And it's a question, I think, of industrial maturity of need. I think the space sector today is just evolving faster now because there's more impact on what we do. So, because the launch costs being reduced, anytime you solve something, it's not just for space exploration, it's also for you can bring more value. There's so much value you can bring with a single satellite that costs, a billion a piece. Being able to say, oh, we're going to launch for the same billion, we're going to launch, hundreds of those. It changes the way, people start to think about what space is good for. So I think there's a lot of reasons for that. There's a lot of very interesting, very challenging engineering. And today there's an acceleration of that engineering also. So it's like maybe we would have gone to that point even in a slower pace without this acceleration of space. But at the moment, the acceleration of space is clearly giving more, energy, more impetus to actually, make those solutions appear. So I see this, we talked about the speed of innovation in space. I think it also comes down to a shift from space programs for exploration and military to commercial. And commercial scale means that you have far more impact. You've got it's becoming more impactful on our lives. And as a result, there's more demand for development and solving those problems.
Yeah, no, I mean, fully agreed. Of course, and actually, I would agree because I run a space venture capital fund. I very much believe this. But I mean, I think I assume you're seeing the same thing. So, because at the end of the day, the demand for your product is driven by the amount of data that has to move back and forth between Earth and space. And from what we're seeing, both on the communications as well as on the Earth observation side, well, let's just take Earth observation for a start. I think we're going to see this, or maybe already seeing the same sort of data explosion we've seen on the ground, right? Like, ever more data is being produced in space. I mean, it seems like ever more Earth observation satellites are going up, like in numbers, right? But then also the types of satellites that are going up. I mean, now we're like having like hyperspectral satellites with hundreds of bands. I mean, the amount of data that's being produced is just like ridiculous.
Yeah, I agree.
And so, I mean, of course, interesting question, sort of like how much, of this will be solved by onboard computing, which is also sort of a parallel development, but you still probably want to bring a lot of data back, right? So
yeah, I think that this for Earth observation is very, very good point. Today, we're already like the way you bring data down is already a bottleneck for Earth observation satellites, and not for the next generation ones, the ones that are already flying.
Yeah.
And yes, everybody's working on, okay, I'm gonna go to higher data rates RF, I'm gonna include more data relay, I'm going to go to optical, and I'm going to include some, in onboard processing in order to reduce the amount of data. And all of that has like, pros and cons. So there's not like a single silver bullet solution. You mentioned the, inboard processing, especially, like, oh, I'm detecting something that looks like a tank. I'm going to take a video of that to know which direction it's driving and how far it's going, for example. I mean, that's kind of a very, very good use case. Like, you're gathering more information based on something so you don't really have time to go down, and you don't have time to process on the ground, so you need to do it there. That's, for me, it's kind of an obvious case where onboard data processing is extremely valuable. On the other hand, from the discussions I had with some, different people in intelligence, they really want to have access to the raw data. It's very important for many, many reasons, but it's very, very important. Like the situation where, there's such a crazy onboard processing that they just give you a list of, oh yeah, I took a picture. I'm not giving you the picture, but I can tell you there's a list of, these are the number of plane on that, place, and the number of cars. And I mean, like, going there, it's like, people would freak out because they, imagine you have to make a massive decision based on that. You want to check,
I was going to say, it depends on the magnitude of decision, right? It's sort of like, you want to like, oh, we received a text message from the satellites that our adversary launched a nuclear missile. It's like,
So I think the having access to the raw data is going to be like, so my point is more like, I think you can make smarter satellites that will enable you to gather more data, no problem there. But having smarter satellite that will enable you to reduce the amount of data that's flowing, that's a good story. And maybe it's true in some cases, but I would say in a lot of cases, it's not going to be like, it's more going to be like, people want to check, people want to have, like, how much trust can you put into the system, especially in contexts where the decisions are so important. It's not like massive magnitude. You've got, people's lives are at risk. So you want to check things. And so I think that's one angle there. Space data relay is another good one. You want to, instead of waiting for going on top of a ground station, you want to you send your data typically with an optical link to another satellite that's already on top of ground stations, so you can get it down. I think that's a very, like, it works well in order to bring down more data, and especially bring it down faster. But what we've done, especially in some calculation, we just realized that, well, if you do this and you really want to use your satellite as much as as you can capture, you end up in a situation that you're monopolizing another, satellite, that you're basically paying for two. And that starts to be like, oh, can I afford that? That's actually quite a lot of money in some cases, like space data relay situation. And so then the question of, okay, should I bring it down with optical? That's another option. Is there enough optical ground station to do that? So there's a lot of players building those ground station network that you can go there. But it's going to be a combination of factors. But yes, that data demand of Earth observation is going through the roof at the moment. And that's for the satellites that are already flying. So it's not even think about the ones that are being designed right now that just require crazy stuff.
Yeah. So, okay, taking a step back, so not just Earth observation, but also its communications and any other use case you can think of. Where do you see the main demand driver in the market right now for space to ground optical, and where do you see it maybe in like 5 or 10 years? Because then there's some other interesting things I want to sort of quickly tease your brain on, like, current talk on space data centers, and that kind of thing.
I think honestly, today I would say there's a strong recognition that the jamming is part of life now in conflicts, and having optical links that are non-jammable is extremely important. And non-jammable, no interception, no detection, no need for spectrum. So not the capacity angle of the optical, but the
safety,
the sovereignty, the safety angle of optical. I think this is where I see a big chunk of demand. And because there's like this recognition that, yes, we need a solution to that problem. Otherwise, we're like, we are relying so much on radio for everything we do that when radio is not available anymore, there are a lot of things that, a lot of smart systems and things like that just don't work. And so this sovereign push onto, yes, we need to have a solution that is, so it's, it's how do you make a secure transmission? How do you ensure there's always a working transmission, basically? And that's really tough. So optical as one of the channels that you've got available is a very, very good solution for that. And then that's probably what happens today. And if you look at 5 years in the future, what we might see is a complete shift on this. And it's like, the cost per bit for optical is much lower than for RF. And so basically, while at the beginning there might be more demand on a safe link, in the future, it might be just a question of, it's just cheaper to go optical, so let's go there. And I think we're going to see those kind of 2 main drivers for optical to the ground grow. In the short term, I would say the safety, the security of the link aspect is probably stronger, but the high data rate and low cost per bit angle is probably going to, it's catching up, basically.
Okay, so which then obviously means in the near term, it sounds like more sort of sovereign defense, national security demand, and then in the medium term, it would shift over into commercial. Commercial
something like that. Yeah.
Where do you think let's say like 10 years or so, the ultimate architecture would go? Do you think we're going towards like majority optical? Because the spectrum thing you mentioned, that's like real, right? I mean, it seems like it's becoming like a really scarce resource. So if some of the listeners haven't seen this, just as an example, there was a recent deal where SpaceX, it was a very special case, but SpaceX acquired the spectrum they need basically for their communications between their satellites and devices on the ground, and they paid over $18 billion for that, right? So spectrum seems becoming very scarce and very, very expensive.
I think I read 17, but we're talking about the same price and the same EcoStar SpaceX.
A lot of money.
Yeah, it's a lot of money. Yeah. And it's interesting because the way people will behave after that is basically give the price to what spectrum, is how much is it worth. So when you design your architecture, you might start to think, okay, maybe I can release that part of my spectrum and sell it to somebody else. And so I'm going to be maybe using a bit more optical so that this, part of my network requires less spectrum. Or, I'm pretty sure, I would say, I don't know, I'm not sure, I've not done those calculations, but I'm pretty sure we will be using as much of the spectrum as possible. Like it's going to be like a default situation. We're going to saturate spectrum, saturate the bands with what we want to use it for. And then, the rest, all the thing we want to carry on top of that needs to be with something else, which would be optical in this situation. And for example, if you just think about, okay, maybe, direct to device, like if it's point to multi-point, I mean, radio is much better than optical. A tight beam is a tight beam. So, it's like So if it's point to multiple, you're broadcasting, you need radio. So maybe in the future, you're going to have a lot of radio on those kind of setup, like point to multi-point, and then a bit less on point to point. And you're going to have like a very fundamental kind of split of when you use optical, when you use RF. I think that's a very, very high level stuff. But you could also imagine that you've got more and more optical on when you go high data rate, and radio comes in as a backup or as an hybrid. Honestly, my take on this is not going to be optical is going to take over. It's more going to be in a hybrid situation where there's going to be some optical and some radio. And we're going to be leveraging the fact that they don't have the same kind of challenges and the same benefits. So just basically the sum is going to be better than each of them. But that's what I see in the future. But the question of spectrum is a very, very good one. And people need to keep in mind that there's a direct competitor to spectrum, which is, to space user spectrum is this thing, our mobile phones. Those use a lot of spectrum, and basically there's so much money on those that it's very, especially on the ground level, that it's very likely that, it's the pressure, it always goes against space. It's not in favor of space. It's more against space. So if you go if we need to unlock new bands for a mobile phone spectrum, where do you take it? Who gives it out?
Yeah.
Is it going to be military? Is it going to be space assets? But it's not going to be like, oh, there's going to be a new free band for space assets. Because if you've got a new free band of spectrum, you're going to give it to mobile operators first.
Yeah. Understood. So how about just one specific case I'm curious about, like in-flight connectivity, right? Because then it's like to one object, so I guess the tight beam would work.
Oh, yeah, definitely. Yeah.
But it's a moving object. Does that complicate things, or is
I mean,
that
when you
feasible
think
today?
about it, satellite to satellite is moving, two satellites moving.
And
So that's
actually extremely much faster, you're right.
Yes. So I'm just saying, like, so no, I think it's like airplane to satellite is a very good example of something that would work. I mean, it depends also then it's going to be a question of cost, question of how many terminals you put in each satellite, it's congestion. So there's a lot of question there, but yes, it's a very good example. And the two moving objects, satellite to satellite today, they work really well. And it's amazing, especially when there's something called in-plane and cross-plane. So when you've got connections, optical connections, sometimes they connect to a satellite, like one satellite talking to one just in front of it. So it's, relatively, you could assume it's relatively easier. But then they also connect to satellites that are not in front of each other. So it's just completely, and those, like, it's the kind of connection that you would, it's like, they go in almost in opposite direction, different angles, and so they have to track it, and they do it really well.
Yeah, it is really quite impressive. But so, I mean, if SpaceX, I mean, they're having tons of ground stations, right? Like radio ground stations. So do you think that type of thing, and not only SpaceX, right, other constellations as well, do you think that type of thing is going to switch over to optical, or?
It depends. We are involved in discussions on this architecture. What we are seeing at the moment is there's kind of two kinds of shift. There's a shift on the users. So I mean, I've got a military base. I'm thinking about having optical links because I'm afraid of being jammed. There's user terminal, radio for optical for user terminals. And then there's the optical for the gateways, which is what you're mentioning. And this kind of optical for the gateway discussion is something that needs to happen relatively early on the process, because each generation of you design your whole constellation taking everything into account, what the users need, what I've got on satellite, especially what I've got inside the satellite, like the data processing and stuff, and then what I can do on the ground. And you want to match the bottlenecks. You want to avoid to have like an overpowered satellite with a limited bandwidth to the ground, or vice versa. And so yes, we're involved in some of those discussions on using optical as gateways, and that's very interesting. And it's not just, I mean, it's like there's a lot of different constellations. A lot of people think about, okay, is it now? Is it Gen 2? Is it Gen 3? When? It's basically what I'm seeing now is the question is more about when and then if. So it's going to be like, which generation of my constellation does it make sense to have an optical gateways? And is it going to be a massive flip, as we said, like a lot of gateways, or is it going to be like just a few? That's kind of, and it's a question of Excel spreadsheets and engineering, basically.
Isn't it always?
Yes, I agree. But that's a good thing. Like you need, when you start to be at that position, say, okay, once you've got this kind of Excel spreadsheet and say, okay, what are my hypotheses? And you say, okay, if this happens, then I need to switch to that, or I need to do that. Yeah. This is a much better situation to be in, because you kind of have a very rational way of saying, this makes sense then, this makes sense now, this makes sense. And you kind of create those trigger, and then you can be very rational, because this allows you to avoid the hype. Yeah. And, hype is sometimes can drive us to do things, but maybe too much. So if you've got very rational things that, at that point in time with that, there's a fundamental way that we need to go in this direction. And what's interesting with optical radio is that there's a moment when basically once you've done that shift, it doesn't go back. So it's like when you look at the analysis, it's like once you pass that threshold, they say, yeah, it's relevant for my specific context and going optical, then 3, 4, 5 years later, it's still relevant. Like, it's not like, there's no way that radio then overtakes optical again with a lower cost, but that doesn't happen.
Right. So, I mean, I'm partly asking out of curiosity, sort of putting on my investor hat, right? Because, I mean, we always get pitched all the time, including from people in this value chain, right? And I mean, there's a number, I mean, I'm sure you're aware, there's a number of people who are working on what I would describe as like better mousetrap for, like, let's say a radio ground station, like, really fancy antennas and stuff.
Yeah.
And I'm listening to you and I'm thinking like, well, is that kind of like, is that even the right path anymore? Or do you think there's room for both?
I mean, it may be. And I mean, there's the fundamental answer to that, which is, point to multi-point radio has a massive benefit. Just the physics means that it's going to be very good. And then point to point, it's so that the first off, there's this angle, and then the second thing is, so on that angle, anybody working on flat panel antenna, for example, because it's highly mobile, it's very that's something that's a very, very smart thing to do, I think. And cheap FPAs is like, I would imagine something in the future where you like an FPA in every single car, that could be kind of a vision on leveraging leveraging space connectivity everywhere.
So you have to, for the non-technical podcast, you have to mention about FPAs.
Yeah. So FPA is a flat panel antenna. So it's instead of having this kind of, we all think about those massive dish that. Yeah. So when you've got this dish that are fixed, it's because they're connected to geo satellites. The geo satellites relative to the Earth is fixed. But the problem is we've got more and more satellites that are not geo, that are not so far away that they can be stable compared to where we are on Earth. So people like the satellite that are LEO, low Earth orbit, they go across and then on top of you. Typically, a satellite goes from horizon to horizon in 8 minutes. Mm-hmm. And so you need to track it. And you can track it with this kind of parabola that just moves around, but then you've got a motor, then you've got some, it's actually quite costly. And the other option is this amazing stuff called flat panel antenna, which is like it's just tracked with electronics. So you've got this fixed surface, and that fixed surface there's a correction on a lot of small sensors, and you just basically combine the signals from those small sensors in a proper way. This gives you like the equivalent to tracking. And this is magical. Like for me, I love this technology, and this allows you to connect basically to LEO and track things. And sometimes I think I've seen flat panel antenna with multi-tracking stuff at the same time. It's like that's great, and I think that's kind of that's extremely powerful technology basically. And on that angle, I would say optical is not going to be there for that for quite some time. And so I think that optical is going to be on point to point definitely, and it's going to be very strong on point to point, but point to multi-point or this kind of very mobile scenarios, it's going to be probably less deployed there, definitely. So if you're doing R&D in very high speed, like pushing radio to very high data rates, crazy new bands, I would say it all comes down to how easy it is. So if you need to reinvent all semiconductor industry just to get to that new band and get new amplifiers, which I know there are some bands a little bit like that, I would say, well, I would be in your position and say, well, maybe that's too much for this new mousetrap. But if you've got it's more like a question of return on investment on that one.
Okay, understood. So let me ask you, but if we go towards a future where not everything, but hopefully a lot will switch to optical comms, is there any... Okay, so the tech seems to be there now. The market demand is there. Is there any other sort of remaining obstacles or things to solve on the way to adoption?
The obvious one is risk. So we are coming from a situation where satellite optical to ground was perceived as something extremely risky. I've seen so many failed thing that didn't work out and stuff like that. So we at Cailabs, our role is to basically show, demonstrate, test, and test to show people, yes, the risk is reducing or has been reduced quite a lot and is still reducing. This also, we are working on industrializing the product, making them, the goal is to make optical as routine as radio. And it's a lot of, basically it's something that needs to improve because we've been using radio for 50 years, Sputnik basically. And so, before that you had this kind of film, but then, Sputnik was a radio signal. And my point there is to say, this is very established technology, and it's not just making it work that in order to change the industry or to have that add that to the industry, you also need to make it smooth into how people will use it. So deployment needs to be smooth. Supply chain needs to be smooth. If it's like, I can make 2 a year, then I'm not going to make a dent into the ecosystem. This is why we're investing. We've got we've got a new factory coming up with a 50 ground station a year capability. We are scaling up production in other things, securing parts of our supply chain. We are investing in deployments, so installation, maintenance, all of that basically in order so that it's like a one-stop shop. It's an easy process for our clients. We're also investing in remote operations so that our clients, at least at the beginning, can be supported. It's like, don't worry about it. We'll just take, we can help you on this. We can take control. If you're not if you don't have the people, if you are like you train, we also do some training. So all of that needs to happen, and it's like a shift in the industry, or it's an addition to the industry. So this part is like less risky overall because it will happen, but you need to do that in order to have a big impact.
Gotcha. So following up on that, so on the risk part though, I mean, maybe I'm being naive here, but if you're starting sort of right now, sort of focus from defense, like defense national security satellites, I mean, wouldn't they want to have like a backup radio payload for redundancy on board?
Yeah, obviously, yes. Yeah, I mean, there's going to be a hybrid. So yes, that's kind of one of the solution where you reduce your risk. And then you come down to also, what is the risk of jamming? And the risk of jamming for those clients tend to be 100%. Like they will have jamming. so you've got a point like,
the world we live in.
It's optical, it's new, yes, but my risk is 100%. So I need to do something. And so I think it's also like a frame of thinking, like, oh, actually, like I'm gonna, I'm maybe so optical is becoming more and more industrial and more deployable, fast, solid, routine. And somebody who's extremely afraid of being jammed should look at it very early, because this risk of jamming is 100%. So it's extremely important that they get in very fast. And somebody who's not afraid to be jammed can wait. It's less less urgent. They should let the others, the ones that are really afraid of being jammed, to actually go first. And that's going to be I think it's going to be a very interesting market dynamics. I mean, we love to be in that position.
Sure. And you mentioned the supply chain.
Yeah.
I think I overheard in another conversation with Optical that some of these the components use like rare earths even. But are there any supply chain issues, or do you think it's relatively secure?
It's not rare earth issues, but there are, like, especially the volume that's needed for optical ground station. The fact that I mean, you mentioned it, like I cannot give any like public information, but like the number of ground stations needed is much higher than the number of observatories today. And so the question of, is there enough telescopes, is there enough domes, is there enough like different elements that were designed by observatories? So basically the good thing is there are a lot of people that can do those things, but then it's usually one-off to 1-2 units. So you need to solidify that manufacturing so that it can actually be a very solid product there. And that's kind of the broad kind of and it's not just those very big items. It's like, it's a new product, it's a new technology piece. So you need to make sure that those can climb in volume. And this is part of our investment plan. We are making sure that the different elements, and there's a differentiated aspect to that. So some things, that's going to go up in volume, and you just need to have enough suppliers that take care of that. And other pieces, like, okay, yes, this one is not going to naturally go up in volume. So what can I do for that?
Understood. And while you were mentioning sort of like a high number of ground stations, I forgot to ask you, like with your technology, is it like, let's call it location agnostic? Or I remember I was having some of these conversations a few years ago, and some people were like, yeah, optical, but it's not trivial to go through the atmosphere, as we discussed. Hence, we're going to put it on top of the Andes Mountains or something.
Yeah, and
that doesn't sound very scalable.
Yes. So I think, if you don't deal with the twinkling, then it becomes your solution. Oh, I'm going to put it somewhere, top of a mountain. And when you deal with twinkling, you don't care. Like today, our ground station is located on the ground near Rennes. So Rennes is a city in the one we work on the most. The other deployments we've got, it's all not high basically, but you need to deal with twinkling if you wanna be able to locate that into locations that is not crazy high mountain stuff. And I think when you look at the whole system, putting it high in the mountain, the problem is to bring capacity and bring the optical fibers to get there, because you need, I mean, optical ground station is 10 gigabit per second today and is going to 100 gigabit per second in the future. 100 gigabit per second is like, you need a good fiber there. You need, and so fiber, 100 gigabit fiber, so it's basically dark fiber to the top of the mountain, that's cost far more than the anti-twinkling stuff, basically. Let's put it this way. So my vision on this is, you need the optical ground station to be in locations where there's not too much clouds, but they can be close to a city, no question there. And so for us, it's like, there's great location in Spain, Italy, Greece, location Middle East, Australia is good too, and south of the US, definitely. So all of that basic location is no problem there.
Okay, perfect. Okay, switching gears as we only have a few minutes left. So you mentioned a little bit about your future plans, expanding production capacity. I was going to ask you, you guys just very recently raised a 50, I think it's 57 million euro
Yes,
funding
yes,
round.
that's right.
Congratulations. I mean, it's a great round, especially for Europe. So I guess those are some of the ways in which you use the money is
Yes.
expanding production capacity.
Yeah, so basically it's half of our investment plan goes into expanding supply chain and production capacity, targeting this kind of 50 optical ground station a year milestone from next year, from 2027, sorry, to clarify. So I'm already thinking we are in 2026, sorry. And then a third of that investment goes into some of the technical advancements. So for example, transportable ground station is a big piece that we want to push for. Same thing for multi-orbit, LEO, MEO, GEO. There's some things that we want to improve, and also moving higher data rates. So today our bread and butter is 10 gig. We want to be able to go 100 gig or more. And we already do 100 gig validations on some subsystems, but like integrating that fully into the full ground station is something important for us. So that's kind of where we're investing. And there's the remainder of that money is basically being able to sell more efficiently all around the world. And part of that is basically demoing. So our style of sale, is we basically show people. We don't do slides. I'm not good at doing a keynote, on a desk with big words behind and music. We show results, and that's what we do. And so a lot of our work is to make sure that we've got these amazing results and we show those results and people get convinced by those results. So we need to be there. We need to be able to provide demos. We need to invite people to see those, and we need to be able to bring the equipment when it's needed to the clients, so that they have a way to check, to see it in their location. So that's kind of the remainder of the investment.
Okay. And so if everything goes to plan and keeps going to plan, like 10 years down the road or so, what do you think Cailabs will look like? What do you want it to look like?
What I want is us to be like the main manufacturers of optical ground stations. And I want us to be like, we are there and we are a company, people rely on. We produce a lot of ground station every year because, by that time, the market is adopted that, and, it takes its role, in parallel with radio. So it's relatively significant. We sell both transportable and fixed optical ground stations. We, at that point, 100 gigabit, 200, 300 gigabit per second is routine. So it's a normal thing. And we're basically, Cailabs is a good stakeholder in this kind of news, how we use space in the world. And I think that would be my dream.
Okay, good stuff. So we always have the same last. Oh no, actually, I'm just going through a list of questions. There was one question I forgot to ask you. Usually, I would have just forgotten about it now, but I'm actually curious, which is, so what would happen if I somehow kind of walked as a pedestrian in between like the station and the tide beam and looked up? Is it like is it dangerous in any way, or is it like a supermarket type laser?
Yeah, it's a very good point. It's eye safe. So that's a big requirement on everything we do. We need to be eye safe.
Okay.
Eye safe is a legal requirement that is the same in all countries. It's actually basically it's the same level of safety than the laser pointer you can buy in a supermarket, except that we don't see it. Like, it's not even the red dot that you see, but it's like the same level of security of that. So it's yeah. And on top of this, some of those laser pointers, sometimes they come from countries where they don't really check that much. So they might be actually a little bit dangerous in some of those, because there's so much more effort to make sure that so it's more like, it's safer, I would say, arguably safer than the one that you can have, in open market. It's extremely important because you don't want an optical ground station to distract an aircraft pilot, for example.
Yeah.
So it's invisible. The aircraft pilot will never see it, and it will never be a problem for the eyes.
Yeah. Suddenly you have like some, you said it's invisible, like some red dot on the ground, and you have tons of cats chasing. No, I'm kidding.
That would be awesome. I agree with you. But the wavelength, the color that's been chosen is invisible to the eye. It's because it's the same wavelength, same color as what we use in telecom fiber, so we can leverage like the standard. It's actually good. We're going with that standard because it can leverage a lot of the ecosystem that is being deployed for telecom. So I think it makes a lot of sense to go there. But that wavelength is completely, it's invisible. It's 1550 nanometer for the people that, of your listeners that, know that.
Okay. All right. Now, really the traditional final question, which is about science fiction. And the question is always like, you like science fiction? And if yes, would like to suggest a favorite movie, book, TV series. But before we get to that actual question, I have an extension question, again, I'm listening to all of this and the advantages of optical communications. And then, I'm a huge fan of the, search for extraterrestrial life and extraterrestrial intelligent life particularly, right? And then I'm like, SETI, breakthrough listen. I mean, for all I understand, maybe there's some information I don't have. They're looking for radio signals. It's like, are we like limiting ourselves to like really primitive, intelligent civilizations that haven't discovered optical yet? Or like,
I haven't thought about it. In a way, yes, but I would say also if you're like, okay, that this like you can have, okay, maybe why don't we think that there would be like somebody with a very highly advanced society would actually broadcast themselves and say, hey, we are here, so that you can create that connection. So I've got no clue. I think there's a lot of
you're right.
debate
Maybe
on
they
this,
think
like,
like, okay, we're using like optical, or maybe it's some weird quantum coming. I don't know. We're using this now, but there's for the other more primitive civilizations in the universe. Let's broadband on radio too.
Yeah, for example, or you could actually say, well, radio goes in all directions, rather
so
than,
it's more efficient, like you described.
Yes, like for example, you could imagine looking at, but we already, if you think about it, we're already doing that because we expect the extraterrestrial intelligence to be close to stars, I think, obviously, and we're already looking at those stars with our telescope observations, stuff like that. And I'm pretty sure if we saw like Morse codes coming from Alpha Centauri, even in optical, we would pick it up. And I mean, I don't know exactly there, but like I would say, because I think a telescope directed to a nearby star or whatever, you basically, this is a very small part of the whole, whole sky. You are focusing somewhere. So if there was a source of light there, it's a very, very good question, honestly. I don't know. I haven't thought about that.
I need to get someone from SETI on and like.
Yeah, you should. That's good idea.
Yeah.
But yeah.
Anyway, final question.
Yeah. It's
like,
the culture series. Ian Banks. Yeah. I mean, it's obvious. I love that one. So it's probably like it's the best.
That's a great one. Also, Elon is a big fan of that. Quite okay, Jeff, thanks so much. It was a really interesting conversation. Nice. Best of luck on the investments now and expansion. Very excited, and maybe we'll pick this up again in 2 or 3 years and see where you've gotten to.
That'd be great. Thank you.
Right.
Thank you for the discussion.
Thanks so
amazing.
Much.
Cheers.
And that's it for another nominal episode of the Space Business Podcast. And once more, if you enjoyed this episode, please leave us a 5-star rating on your favorite podcast platform, such as Apple or Spotify. You can follow us on Twitter at podcast_space. We're also on LinkedIn under the Space Business Podcast. Lastly, if you have any feedback, including ideas for guests, and that may even include yourself if you have an exciting space story to tell, or interested in becoming a sponsor, or really for any other suggestions, you can drop us an email at spacebusinesspodcast@gmail.com. Thanks so much for listening, and see you for the next episode.